Number 1. Liangzhu Megaflood, a hydraulic civilization drowned by its own landscape. Picture a city where every street ends at a canal. Around 2300 BCE in the lower Yangtze Basin near modern Hangzhou, a late Neolithic society called Liangzhu was doing something remarkable. They were not a loose collection of rice villages. They were an urban rice farming state organized around water control on a scale that would not look out of place in early Mesopotamia. The terrain was low, flat, and waterlogged. The Taihu Plain is essentially a sponge. Building a city there required engineering solutions that took generations to refine. At the heart of Liangzhu sat Mojiaoshan, a raised earthen platform that served political, ritual, and administrative functions. Think of it as a state house lifted above the floodplain. Around it stretched walls, canals, levees, dams, reservoirs, and wetland control systems. Archaeologists working in the area have mapped at least 11 dams in the upper watershed alone. These dams formed a tiered hydraulic network designed to manage seasonal water flow. In modern terms, Liangzhu had built something like a flood control authority 3,000 years before the Romans paved their first aqueduct. Power in Liangzhu depended entirely on managing water successfully. Rice agriculture was the economic backbone. Paddies required predictable flooding and predictable drainage. Canals carried grain, people, jade ornaments, and elite goods between districts. Jade itself became the visible currency of authority. The whole system worked because the East Asian monsoon, the major natural force in the region, behaved within expected limits. Then, it stopped behaving. Around 4,300 years before present, the climate window shifted. Speleothem cave records, the technical climate evidence pulled from cave mineral deposits, document an extreme wet interval between roughly 4,345 and 4,324 years before present. That is a 2-decade pulse of intensified rainfall layered onto a system already operating near capacity. The failure mode was not a single instant wave. It was prolonged inundation. Rice paddies stayed underwater. Granaries flooded. Saturated earthen walls and platforms began to weaken structurally, the way a sandcastle softens after the tide turns. The mainstream theory holds that intensified monsoon rainfall simply overwhelmed Liangzhu's hydraulic system. The archaeological reading goes further, suggesting that social authority collapsed when elite water control failed. If your legitimacy comes from keeping the canals working, broken canals break the throne. A more speculative theory proposes that Liangzhu's memory may have seeded later Chinese flood control legends, the stories of Yu the Great taming the rivers. The ruins themselves were buried by sediment, water, and later land use, only rediscovered in the 20th century. Liangzhu shows how innovation built around water can fail when water exceeds design limits. But what happens when the threat does not rise from the sky, but from beneath the ocean floor? On a winter night in 1700, an entire coastline was about to learn that answer. Number 2. Cascadia, 1700 CE megaquake and tsunami. A disaster remembered by trees, sand, and story. The evening was January 26, 1700. Along the Pacific Northwest coast from Vancouver Island down to Northern California, a fault line had been quietly accumulating strain for centuries. That fault is the Cascadia subduction zone, a locked megathrust boundary where the Juan de Fuca oceanic plate slides beneath the North American continental plate. Subduction zones are the engines behind the largest earthquakes on Earth. When they slip enormously. That night, scientists estimate the rupture reached a magnitude somewhere between 8.7 and 9.2. The break likely propagated along most of the roughly 1,000-kilometer fault, end to end. Coastal land dropped suddenly, in some areas by 1 to 2 meters. Forests of western red cedar that had been growing on solid ground found themselves standing in salt water. They died where they stood. We call them ghost forests today. And tree ring dating from their preserved trunks places their death in the winter of 1699 to 1700. The earthquake displaced an enormous volume of seawater. That displacement became a tsunami. Sand sheets from this wave still rest atop marsh and estuary sediments along the coast, sealed in place like pages in a geological book. The wave then crossed the entire Pacific, taking roughly 9 hours to reach Japan. There, on the night of January 27, 1700, coastal villages recorded an unexpected flood with no felt local earthquake. Japanese scholars called it an orphan tsunami. Centuries later, geologist Brian Atwater and his colleagues used those Japanese records to pinpoint the parent earthquake's date almost to the hour. The tsunami did not arrive as one single wall. It came as multiple surges. Indigenous oral traditions among the Salishan, Quileutni, Makah, and related peoples preserve accounts of violent shaking, ocean withdrawal, flooding, and entire villages lost in darkness. At Pachina Bay, on Vancouver Island, the Hu, Aiei Aiki people retained a narrative of a winter night when their lowland village was destroyed and survivors had no time to reach high ground. The mainstream theory describes a full margin megathrust rupture producing regional subsidence and a basin-crossing tsunami. Archaeological readings note that coastal settlement patterns shifted afterward, suggesting communities moved inland or upslope from remembered disaster zones. A more speculative interpretation suggests that some oral accounts may preserve eyewitness-level disaster memory, transmitted with extraordinary precision across roughly 3 centuries. There was no written colonial record of the Pacific Northwest in 1700. The disaster left no European paper trail. It survived only in trees, sand, and story. Cascadia proves that engineering must respect plate boundaries, not just coastlines. But what happens when the disaster source is not under the sea but the side of a mountain collapsing into it? For that, we travel to the eastern Mediterranean. Number 3, Etna East Flank Tsunami, the possible Sicilian wave that reached the Levant. This case is contested, and the contest is part of what makes it interesting. Around 8,300 years before present, roughly 6,300 to 6,000 BCE, something happened on the eastern flank of Mount Etna in Sicily. Etna is one of the most actively studied volcanoes in the world. Its slopes are unstable, slowly creeping toward the sea under their own weight. A flank collapse is when an entire side of the volcano fails as a massive landslide. The volume involved can reach tens of cubic kilometers of rock. When that massive rock enters water, it displaces an enormous volume of sea. The result is a flank collapse tsunami, mechanically distinct from a storm surge or an ordinary earthquake-driven tsunami. Numerical modeling by researchers, including Maria Peresky and her colleagues, suggests waves from this proposed Etna collapse could have crossed the eastern Mediterranean within hours, reaching the Levantine coast at heights of several meters. That brings us to Atlit Yam, a submerged late pre-pottery Neolithic B and C settlement off Israel's Carmel coast. Atlit Yam was substantial, covering several hectares, large for its period. Excavations led by Ehud Galili have revealed houses, freshwater wells, burials arranged in deliberate patterns, stone installations, and abundant food remains. The economy was mixed. People farmed grain, herded animals, fished offshore, and gathered shellfish. They stored food. They built things to last. Atlit Yam existed during the long Holocene sea level rise, when global meltwater was still pushing coastlines inland. A tsunami arriving at such a settlement could have done immediate physical damage, smashing buildings and sweeping out tools. It could also have done invisible long-term damage by contaminating the freshwater wells with seawater and salinizing the surrounding fields. A community that loses its drinking water and its growing soil in one afternoon faces a problem no Neolithic technology could solve. The mainstream theory still holds that Atlit Yam was mostly lost to gradual Holocene sea level rise rather than a single catastrophe. The archaeological reading suggests a sudden tsunami may explain the apparent rapidity of abandonment. A speculative interpretation, popular but unproven, ties broader Mediterranean flood memories to events of this kind. The evidence problem is real. Underwater tsunami deposits are extremely difficult to isolate from other marine sediments. The site itself sank beneath the sea and was preserved largely by accident. Coastal innovation always depends on a bargain with unstable shorelines. Sometimes that bargain is renegotiated by a wave. But shorelines are not the only places where the ground can betray you. Sometimes the betrayal comes from below, in the form of a mountain that has been quiet for 1,000 years. Number 4. Avellino, Eruption. The Bronze Age, Pompeii, before Pompeii. Almost everyone has heard of Pompeii, buried by Vesuvius in 79 CE. Far fewer people know that Vesuvius did almost the same thing nearly 2,000 years earlier. The Avellino eruption, dated to approximately 1995 BCE plus or minus 10 years, was a Plinian event from Soma Vesuvius in Campania. The deposit it produced is called the Pomici di Avellino, the Avellino Pumice. A Plinian eruption gets its name from Pliny the Younger, who described the 79 CE event. The defining feature is a vertical eruptive column of ash, gas, and pumice rising tens of kilometers into the stratosphere. The Avellino column did exactly that, but in a Bronze Age landscape rather than a Roman one. The affected communities belong to the Palma Campania culture, an early Apennine Bronze Age tradition. The site that earned the nickname Bronze Age Pompeii is Nola Croce del Papa. Excavated under the direction of Giuseppe Vecchio, the site preserved entire huts, domestic tools, ceramic vessels, and even pens with animal remains. Most strikingly, footprints were preserved in the ash, frozen mid-stride. They are direct evidence of human flight. Hoofprints alongside them record livestock being driven out at the same moment. Whole families left dinner on the table, gathered their animals, and ran. The eruption sequence followed a recognizable pattern. First, pumice fall buried roofs, fields, and storage areas under meters of light volcanic rock. Then pyroclastic surges arrived, fast-moving ground, hugging currents of hot gas and ash that move at hurricane speeds and reach hundreds of degrees Celsius. Ash smothered crops, orchards, pastures, and water sources. Lahars, which are volcanic mudflows of reworked debris, then moved through drainage systems, reshaping valleys and burying lower elevation sites under additional sediment. The mainstream theory holds that the eruption forced evacuation and produced long-term abandonment of the most affected zones. The archaeological reading is more nuanced, noting that communities survived by relocating beyond the devastation radius, often appearing later in the settlement record under modified material cultures. A speculative theory suggests that prehistoric memory of Vesuvius may have shaped later Italian volcanic fear, contributing to the ritual landscape that surrounded the mountain in classical antiquity. The Avellino ash layer itself functions as a chronological marker, used by archaeologists to date Bronze Age sites across central and southern Italy. Volcanic soil can create extraordinary fertility. The same chemistry that erases a landscape can rebuild it within a generation. But not every eruption produces a recoverable landscape. Sometimes the eruption happens in the ocean itself, and the rules change. Number 5. Kikai-Akahoya eruption, the volcano that turned the sea into a pyroclastic pathway. Around 7,300 calibrated years before present, approximately 5,300 BCE, a caldera south of Kyushu, Japan, produced one of the largest eruptions of the entire Holocene epoch. The Kikai caldera is mostly underwater, which makes it both spectacular and difficult to study. The Akahoya eruption is generally classified as VEI7 on the Volcanic Explosivity Index, the same tier as Tamborar in 1815. Recent volume estimates published by researchers including Nobukazu Siyama and his colleagues place the dense rock equivalent at roughly 133 to 183 cubic kilometers. To 83 cubic kilometers. To translate that into modern scale, that is enough material to bury the entire greater Tokyo metropolitan area under tens of meters of volcanic rock. It dwarfs the 1980 Mount St. Helens eruption by more than 100-fold. The ocean setting made the hazard fundamentally unusual. Pyroclastic flows from Kikai entered the sea and continued moving. They became submarine density currents, underwater rivers of hot volcanic material that spread across the seafloor. Seafloor surveys have mapped these deposits across more than 4,500 square kilometers. Above the water, Akahoya tephra spread across much of southern and central Japan, leaving an ash layer that archaeologists now use as a regional time marker. The affected people were southern Kyushu Jomon communities. The Jomon were Japan's pre-agricultural people, with lifeways based on hunting, gathering, intensive fishing, shellfish harvesting, and one of the world's earliest pottery traditions. Near the volcano, pyroclastic flows caused immediate destruction. Beyond that zone, the ecological shock to forests, freshwater systems, plants, and animal habitats was severe and prolonged. Recovery of forest cover took centuries. The mainstream theory holds that the eruption caused regional devastation but not regional extinction. Jomon culture continued elsewhere in Japan, and Kyushu was eventually repopulated. The archaeological reading points to shell middens and tool patterns showing measurable adaptation after the disaster, including shifts in coastal exploitation strategies. A more speculative theory suggests that oral or mythic volcanic memory may have survived in later island traditions, although direct evidence is thin. Knowledge loss occurred because ash buried the affected landscapes, and later, cultural recovery blurred the line between rupture and continuity. The sea, it turns out, can become a transport system for both life and destruction. But not every catastrophe leaves a clear geological signature. Some disasters travel through the body itself, written only in DNA, invisible until modern science learned to read it. Number 6. Frälsegården, plague burial, a family tree rewritten by ancient disease. Around 3300 to 2900 BCE in the Falbygden region of southwestern Sweden, funnelbeaker culture farmers were burying their dead in passage graves. These were collective tombs, carefully built stone chambers used by extended kin groups across multiple generations. Frälsegården is one such tomb. It looks from the outside like an ordinary Neolithic monument. What it contained, however, has rewritten our understanding of European prehistory. The funnelbeaker culture represents one of Northern Europe's earliest farming traditions. They cleared forests, raised cattle, grew cereals, and built monumental tombs that signaled territorial continuity. The Frälsegården passage grave was not an emergency plague pit, it was a planned communal tomb, yet the bones inside told a story no one expected. Ancient DNA work led by researchers at the University of Copenhagen, including Frederick Searsholm and colleagues, recovered Yersinia pestis, the bacterium responsible for plague, from skeletal remains. The study examined more than 100 Scandinavian Neolithic individuals. At least 17% showed evidence of plague infection. From the Frälsegården remains, researchers reconstructed a 6th-generation family pedigree of 38 individuals. That pedigree showed plague appearing repeatedly across roughly 120 years. The plague strains evolved through these successive generations. This was not modern bubonic plague. Early Yersinia pestis lacked some of the genetic features that allow flea-borne transmission, so the disease may have spread through human contact, lice, or other close routes. The risk environment was perfectly suited to such transmission. Shared tombs meant repeated exposure to the bodies of the dead. Tight kinship networks meant that infection at one farmstead could rapidly reach related households. Marriage networks linked communities across distances. The mainstream theory now holds that plague contributed significantly to the Neolithic population decline observed in Northern Europe between roughly 3200 and 2800 BCE. The archaeological reading places disease alongside other factors, including soil exhaustion, famine, low-level violence, and migration pressure from incoming Yamnaya-related populations. A more speculative theory proposes that epidemic trauma may explain abrupt changes in ritual practice and demographic structure that previously seemed mysterious. The disease left no monument until DNA made it readable. Farming innovation created density. Density created new biological risks. That trade-off has repeated itself in every subsequent agricultural revolution, but not every catastrophe is bacterial, geological, or atmospheric. Some are alleged to have come from much further away, and they remain among the most controversial proposals in modern archaeology. Number 7. Younger Dryas impact, the controversial catastrophe at the edge of Clovis. Around 12,800 to 12,900 years before present, North America experienced an abrupt climate reversal. The Younger Dryas was a roughly 1,200-year cooling period that interrupted the warming trend at the end of the last ice age. Glaciers re-advanced. Vegetation zones shifted. The cooling itself is not in question. It is well documented in ice cores, lake sediments, and pollen records worldwide. What is in question is the cause. A group of researchers, including Richard Firestone and James Kennett, have proposed the Younger Dryas impact hypothesis. The proposal is that a cometary debris swarm or airburst event triggered the cooling. The cited evidence comes from a thin sedimentary layer called the Younger Dryas boundary. Within it, advocates of the hypothesis report elevated levels of microspherules, nanodiamonds, platinum, charcoal, and melt glass. An airburst is an atmospheric explosion of an incoming object similar to the Tunguska event of 1908, but on a much larger scale. It would not necessarily produce a major impact crater. The proposed effects include continent-scale wildfires, atmospheric dust loading, accelerated cooling, and ecological disruption. Around the same time, the Clovis archaeological complex underwent a major transformation. Clovis is a Paleo-Indian technological tradition, not a city civilization. It is defined primarily by Clovis points, distinctive fluted stone projectile points associated with hunting large game, including mammoth and mastodon. Clovis appears across much of North America and ends near the Younger Dryas onset. Many megafaunal species, including mammoths, mastodons, and giant ground sloths, declined or disappeared during this same window. Critically, humans did not vanish from North America. Folsom and other regional traditions emerged from the post-Clovis landscape. The continent remained inhabited. The mainstream theory explains the Younger Dryas through a meltwater-driven shutdown of North Atlantic circulation, with megafaunal losses driven by combined climate change and human hunting pressure. The archaeological reading sees Clovis reorganizing into regional post-Clovis traditions in response to changing prey and environmental conditions. The fringe theory holds that comet airbursts triggered rapid ecological and cultural shock. The crater problem is significant. No universally accepted impact crater has been identified for the proposed event. Knowledge loss is severe in this case because mobile hunter-gatherer archaeology leaves sparse, scattered evidence compared to settled urban sites. This story leaves the viewer with a question rather than a verdict. That is honest history. Some catastrophes, however, leave evidence that is unambiguous, even when the world they destroyed is now hidden beneath the ocean. Number 8. Storegga Slide Tsunami, the wave across a drowning Doggerland. Around 8,150 calibrated years before present, approximately 6,225 BCE, a section of the Norwegian continental margin gave way. The Storegga Slide was a massive submarine landslide, one of the largest known in the Holocene. The displaced volume of sediment was enormous, on the order of 3,000 cubic kilometers. When that much material moves underwater, it shoves the sea aside. The shoving generates tsunami waves that radiate outward in all directions. This was not a volcanic event, it was not a tectonic earthquake, it was pure slope failure, possibly triggered by an earthquake or by methane hydrate destabilization at the seafloor. The affected zone included the coasts of Norway, Scotland, the Shetland Islands, eastern Britain, and the entire North Sea basin. Geological evidence comes from layers of marine sand interrupting peat and coastal sediments at sites from Montrose in Scotland to Bergen in Norway. The wave reached estimated heights of 10 to 20 meters in some shoreline locations. To understand what this meant for people, we have to introduce Doggerland. Today, the southern North Sea is open water. 8,000 years ago, much of it was a low-lying landscape between Britain and continental Europe. It included wetlands, tidal flats, river systems, estuaries, and inhabited islands. Mesolithic hunter-gatherer, fisher groups lived there, exploiting fish, shellfish, seals, water birds, plants, and the rich resources of waterway margins. Their camps clustered near shorelines and river mouths, exactly the zones most vulnerable to a tsunami. The immediate impacts would have included drowning, camp destruction, tool loss, and contamination of freshwater sources. Saltwater overwash damaged wetland food systems for years afterward. Fish weirs, shellfish beds, and coastal hunting grounds may have taken a generation to recover, if they recovered at all in their original locations. The mainstream theory holds that Storegga was devastating regionally, but did not single-handedly end Doggerland. Sea level rise was already steadily drowning the territory. The archaeological reading suggests that the tsunami accelerated abandonment of the most vulnerable zones, hastening a process that was already underway. A speculative theory proposes that memories of drowned lands may survive in later northern European flood traditions, although direct cultural continuity is impossible to prove. Many of the relevant sites are now submerged, eroded, or buried offshore, accessible only through marine geophysical survey. Innovation in coastal mobility fails when the map itself disappears. But not every drowned landscape is the result of a single sudden event. Sometimes the question is whether the change was sudden at all, and the answer turns out to depend on which scientists you ask. Number 9. Black Sea Deluge, the flood between geology and myth. The popular date often given is around 5,600 BCE, although estimates vary considerably. The core model proposed in the 1990s by marine geologists William Rain and Walter Pittman of the Lamont Doherty Earth Observatory runs as follows. The Black Sea, they argued, was once a lower freshwater lake, isolated from the Mediterranean. The Bosporus Sill, the narrow strait between modern Istanbul and the Black Sea, acted as a barrier. As global sea levels rose after the last ice age, the Mediterranean eventually breached this barrier. Ryan and Pittman described a marine waterfall, a catastrophic inflow of salt water pouring into the Black Sea basin. In their model, the rate of inflow was extraordinary, raising water levels by tens of centimeters per day and drowning shorelines, river valleys, and Neolithic settlements at remarkable speed. The affected people would have been Neolithic farmers and fishers around the basin, displaced en masse. Ryan and Pittman further proposed that this event could have inspired Near Eastern flood traditions, including the Mesopotamian deluge stories that influenced later biblical accounts. Supporting evidence included marine shells appearing in cores above freshwater deposits, marking a clear ecological transition from fresher to saltier water. The transition itself is real and undisputed. What is disputed is the speed. The key technical question is how low the Black Sea actually was before reconnection. Ryan and Pittman initially proposed a level difference of around 150 meters, which would imply a truly catastrophic refilling. Subsequent work by researchers including Ali Aksu and Liu Gyosan suggests the level difference may have been only about 30 meters, and that the reconnection was slower and more complex, possibly even bidirectional during certain phases. A smaller level difference dramatically weakens the catastrophic version of the story. Adding to the complication, there is no clear evidence of a region-wide population crash that would be expected from a sudden mass displacement event. The mainstream theory now holds that reconnection was real but probably slower or less catastrophic than originally proposed. The archaeological reading allows that local coastal groups may still have been displaced, even under a gradual model. The fringe theory keeps the catastrophic version alive as a potential geological seed for flood mythology. Knowledge loss is acute here, because the strongest archaeological evidence, if it exists, lies on submerged shorelines under tens of meters of water. Myths often form where real environmental change meets human memory, but the Bronze Age Mediterranean world has its own mythic event, one with so much physical evidence that the only question is what it actually did to the civilizations around it. Number 10. The Eruption of Thera, the Aegean blast with a delayed political fuse. The eruption of Thera on the Cycladic island of Santorini has a debated date somewhere in the 17th or 16th century BCE, with broad consensus pointing to around 1600 BCE. Radiocarbon dating, ice core records, and tree ring evidence have produced years of scholarly debate, including notable work by Sturt Manning attempting to refine the chronology. The civilization most directly affected was Minoan palatial Crete, the great maritime power of the Bronze Age Aegean. Thera was a silicic caldera forming eruption with multiple eruptive phases rather than one simple explosion. There were earthquake precursors and small initial eruptions, giving inhabitants warning. The buried Theraean town of Akrotiri preserves frescoes, multi-story buildings, and sophisticated drainage systems, but it does not preserve human bodies or much portable wealth. The absence is telling. The inhabitants apparently evacuated before the main eruption, taking what they could carry. When the main eruption came, it was enormous. The Plinian column dispersed ash across the eastern Mediterranean. Recent volume estimates published by researchers including Tim Druitt place the dense rock equivalent at 34.5 plus or minus 6.8 cubic kilometers, with Tephra as the largest measured erupted component. Pyroclastic flows and surges entered the sea on multiple sides of the island. Tsunami generation came primarily from these sea entry flows and from caldera-related slumping rather than simply from seawater entering a collapsing caldera, a common simplification that more recent modeling has corrected. The tsunami struck the north coast of Crete. At Malea, archaeologists have identified tsunami deposits, including marine sand and fauna, reaching hundreds of meters inland. Harbor facilities, fishing fleets, and coastal warehouses across the Minoan world would have been heavily damaged. Yet Minoan civilization did not end overnight. The palaces at Knossos, Phaistos, and elsewhere continued functioning for decades. The mainstream theory holds that Thera weakened the Minoan coastal economy but did not instantly destroy it. The archaeological reading emphasizes that later Mycenaean dominance from the Greek mainland exploited post-eruption Minoan weakness, eventually replacing Minoan administrative systems on Crete itself within a century or two. A speculative theory popularized by figures from the classical world onward suggests that Thera inspired later Atlantis-like Ort's flood and fire memories. The story Plato told about a vanished island civilization may carry some echo, however distorted, of an actual catastrophe in the Aegean Pass. The most dangerous disasters are sometimes those with delayed consequences. Civilizations rarely fall on the day of the catastrophe. They fall in the years afterward, when the cracks the disaster open slowly widen. We have walked through 10 catastrophes. Now we can step back and ask what they share and what they do not. Catastrophe is not one thing. Each of these events has a different mechanism, a different speed, a different evidence trail, and a different cultural footprint. Looking across the dossier, the most useful comparison is by physical system. 6 of these cases involved flood disasters in some form. Liangzhu, the Black Sea, Storegga, Cascadia, Etna, and Thera all delivered catastrophic water. But the flooding mechanisms were entirely different. Liangzhu was prolonged rainfall inundation, not a wave. Cascadia was earthquake displacement producing a tsunami train of multiple surges. Storegga was landslide displacement with no tectonic rupture involved. Etna was volcanic flank collapse generating a submarine landslide-style wave. Thera was eruption-driven sea entry tsunami generation with a smaller contribution from caldera slumping. The Black Sea, if catastrophic at all, was a marine inflow event rather than a wave. 3 cases involved volcanic systems. Avellino, Kikai-Akahoya, and Thera each illustrate different aspects of explosive volcanism. The Plinian column, the caldera collapse, the pumice fall, and the pyroclastic current are distinct physical processes that often occur in sequence. Kikai-Akahoya is unique in this dossier for its ocean pyroclastic behavior, where flows continued moving as submarine density currents across thousands of square kilometers of seafloor. One case, Frälsegården, illustrates biological catastrophe, plague pressure operating across generations rather than minutes. One case, the Younger Dryas impact hypothesis, illustrates cosmic catastrophe as a contested category. The contrast between sudden events and slow cascades runs throughout. A tsunami arrives in minutes, a monsoon shift unfolds over decades. A plague pedigree spans more than a century. The organizing technical concept is the hazard chain. One trigger produces secondary hazards which produce tertiary effects. An eruption produces ash, which produces lahar, which produces water contamination, which produces famine, which produces migration. A megathrust earthquake produces ground shaking, then subsidence, then tsunami, then saltwater intrusion, then loss of arable land. Lowland coastal societies appear repeatedly in the dossier because settlement exposure matters more than disaster size alone. A modest flood at a vulnerable river mouth can do more damage than a massive event in an empty desert. Direct deaths are only part of the story. Civilizations more often fall through systems failure, through the breakdown of food, water, ritual legitimacy, and trade networks, than through immediate mortality alone. The laws of nature are neutral. Infrastructure decides vulnerability. Knowing that, the question becomes how researchers can read these events at all. The evidence is rarely obvious. The detective work behind every section of this dossier deserves its own examination. Archaeology is reconstruction from partial physical traces. The traces these catastrophes left behind illustrate the modern toolkit beautifully. At Liangzhu, speleothem records, the layered mineral deposits inside caves, function as climate proxies. They preserve isotopic signatures of past rainfall in their growth bands. At Cascadia, tree rings establish the precise season of death for ghost forest cedars, narrowing the disaster to a winter. The ghost forests themselves are evidence of sudden coastal subsidence, since salt water killed trees that had been growing on what was previously dry ground. Tsunami sand sheets, layers of marine sediment trapped in coastal peat or marsh deposits, provide a fingerprint of marine overwash events. They appear in both Cascadia and Storegga records. Japanese historical records of the 1700 orphan tsunami provide long-distance confirmation that tied geological and oral evidence together. At Lityam, by contrast, was preserved by being submerged. Underwater archaeology using systematic diving and sediment sampling has documented the site in extraordinary detail despite its inaccessibility. At Avellino, footprints captured in fresh ash provide behavioral evidence of the moment of disaster, while hoof prints document animal movement during evacuation. The Avellino ash layer itself serves as a regional chronological marker, allowing archaeologists to date sites simply by their stratigraphic relationship to the eruption deposit. Kikai's seafloor deposits required marine geophysical mapping to locate and characterize. The Akahoya tephra functions as a cross-Japan correlation layer, linking sites separated by hundreds of kilometers. Frälsegården demonstrates the most modern technique of all. Ancient DNA extracted from skeletal remains revealed an invisible disease that left no architectural signature. The reconstructed pedigrees showed not just infection, but kinship and epidemic recurrence patterns across generations. Younger Dryas boundary research, with its disputed microspherules and nanodiamonds, illustrates how controversial evidence categories can be, especially when extraordinary claims require extraordinary verification. Storegga sand layers within peat profiles serve as tsunami fingerprints in the North Sea region. Black Sea cores show shells transitioning from freshwater to marine species, capturing an ecological shift even when the speed of that shift remains debated. Thera's tsunami deposits at Malia, with marine sand and fauna found hundreds of meters inland, document coastal wave impact. The absence of bodies at Akrotiri is itself evidence, in this case, of human awareness and successful evacuation. Lost worlds survive through traces that natural processes accidentally preserved, but preservation is only the first step. Interpretation is where the real disagreements begin, and learning to navigate those disagreements is essential to understanding this kind of history. 3 categories of explanation appear throughout this dossier. Mainstream theory is the best supported scientific explanation, grounded in physical evidence and published peer-reviewed research. Archaeological or historical theory is a culture-focused interpretation drawn from settlement evidence, material culture, and reconstructed social patterns. Fringe or speculative theory is a lower certainty, but narratively influential possibility, often invoking mythological echoes or contested mechanisms. These 3 categories produce different readings of every case. For Liangzhu, the mainstream sees climate-driven flooding. The archaeological view focuses on political water control failure. The speculative view connects Liangzhu to mythic Chinese flood memory. For Cascadia, mainstream science describes a megathrust rupture. Archaeology notes settlement avoidance of remembered disaster zones. Speculation argues for precise oral eyewitness continuity across 3 centuries. For Etna, mainstream coastal geology emphasizes slow sea level rise. Archaeology allows for tsunami-driven abandonment. Speculation reaches for Mediterranean disaster memory traditions. For Avellino, mainstream interpretation describes eruption-forced abandonment. Archaeology observes regional relocation. Speculation hints at inherited volcanic trauma. For Kikai, mainstream views describe regional devastation without extinction. Archaeology highlights post-disaster adaptation. Speculation reaches toward island myth memory. For Frälsegården, mainstream science emphasizes plague-driven Neolithic decline. Archaeology integrates plague with multi-factor pressures. Speculation considers ritual panic responses to invisible epidemics. For the Younger Dryas, mainstream science describes climate and human hunting pressure. Archaeology notes cultural reorganization through Folsom and beyond. The fringe view holds on to comet airbursts despite the crater problem. For Storegga, mainstream science records a devastating tsunami. Archaeology sees gradual Doggerland drowning accelerated by the wave. Speculation reaches toward flood folklore. For the Black Sea, mainstream science now favors gradual reconnection. Archaeology allows local displacement. Speculation maintains the mythic deluge origin. For Thera, mainstream science describes slow economic weakening. Archaeology emphasizes Mycenaean opportunism. Speculation suggests Atlantis-like memory. Documentary narration should not overstate weak evidence. Uncertainty can make a story stronger, not weaker, because it shows where active discovery is happening. Conflicting theories often explain different scales of the same event. Cause, trigger, and accelerant are distinct categories. A disaster can trigger collapse without being its underlying cause, or it can accelerate a process already in motion. Treating every disaster as instant extinction is the storyteller's trap. The most honest approach keeps evidence and imagination clearly separated. That separation matters because in many of these cases, the people involved did not actually disappear. What disappeared was the form of their society. That distinction shapes how we should think about collapse itself. Collapse, in archaeological terms, means the loss of institutions rather than the death of all people. The Liangzhu state failed politically after its hydraulic system failed structurally, but the rice farming population of the Yangtze Delta did not vanish. They reorganized into smaller scale communities. Cascadia coastal peoples relocated and adapted, with memory itself functioning as a guide for where not to rebuild. Adlit Yam was abandoned, but the broader Levantine Neolithic continued evolving along higher coastlines. Avellino preserved evacuation rather than mass death. The Palma Campania people moved beyond the devastation zone and reappeared in modified form in the regional record. Kikai-Akahoya's Jomon survivors maintained cultural continuity even after catastrophic ecological shock. Frälsegården shows demographic pressure compounded across multiple generations rather than instant extinction. The funnel-beaker culture eventually gave way to other traditions, but the shift took centuries. Clovis transformed technologically. Folsom and other regional traditions emerged from the same human populations, using new tools suited to a new environment. Doggerland disappeared as a geographic entity, but its population dispersed into Britain and continental Europe, contributing to the genetic and cultural mix of Mesolithic northwestern Europe. The Black Sea region, even under contested displacement scenarios, did not show a regional collapse signature. Thera's eruption produced delayed weakening of Minoan maritime power, eventually opening space for Mycenaean expansion, but the Cretan population persisted under new administration. Several collapse patterns repeat across these cases. Food system collapse appears again and again, whether triggered by ash, salt, or pathogen. Freshwater contamination is a hidden killer in the aftermath of floods and tsunamis, often more damaging than the initial wave. Loss of ritual centers represents political damage, since legitimacy in many ancient societies was tied to specific monumental places. Trade route disruption follows volcanic and coastal disasters, especially in maritime networks like the Aegean. Elite legitimacy fails when the engineering systems supporting elite power, like Liangzhu's dams, visibly stop working. Migration is survival, not defeat. Archaeological absence often means relocation rather than extinction. Disaster compresses decision-making into hours, days, or generations, but human populations are remarkably good at decision-making when they have to be. Civilizations frequently survive physically while losing the form that made them recognizable. The descendants of Liangzhu, farmers, Theran sailors, and Doggerland fishers are still alive somewhere. What ended was the shape of their world, not the line of their genes. That observation leads to a final question. If catastrophe is so often about exposure rather than total destruction, what do these 10 cases together actually teach about innovation, memory, and the limits of human design? The recurring theme across these 10 cases is that humans build by borrowing natural systems. Liangzhu borrowed water and was eventually overwhelmed by water. Cascadia coastal societies lived along shorelines shaped by subduction, and subduction eventually shaped them in return. Adlit Yam used the sea for food and transport until the sea became the threat. Avellino's farmers lived on fertile volcanic ground that was fertile precisely because it was dangerous. Kikai's Jomon world depended on rich coastal and forest ecology, which the eruption disrupted on a regional scale. Frälsegården's farmers gained food security through agriculture, but they also gained population density, and density carries biological cost. Clovis hunters adapted to megafaunal worlds that were already under stress from the warming climate. Doggerland's people lived in a wetland network that sea level eventually erased entirely. Black Sea communities, however, gradually the change unfolded, watched familiar shorelines retreat and saltwater advance. Minoan power depended on ships, harbors, and island networks, which made every Aegean coastline both an asset and a vulnerability. Catastrophe is rarely just destruction, it is exposure. Engineering, ritual, agriculture, and trade all contain assumptions about how natural systems will behave. When climate, plate tectonics, pathogens, or volcanoes shift outside those assumptions, the systems fail. Many of the lost civilizations in this dossier were transformed rather than exterminated. Their memory survives in sediments, in stories, in ruins, in bones, and in myths. The modern relevance is straightforward. Coastal cities still face tsunami and storm surge risk. Hydraulic systems still face climate-driven extreme rainfall. Disease networks still face pathogen evolution under conditions of high human density. Volcanic zones, both well-known like Vesuvius and lesser studied like Kikai, still pose hazards that current engineering can mitigate but cannot eliminate. Subduction zones like Cascadia have continued accumulating strain since 1700, and that strain will eventually release. Innovation is powerful because it uses fundamental laws of nature, the same laws that made canals possible at Liangzhu, that made farming possible at Frälsegården, that made maritime trade possible across the Aegean. Those laws do not change. They permit construction within certain limits, and they enforce those limits without warning when conditions exceed design parameters. The same laws that make civilization possible also define the limits civilization cannot negotiate with.